In Lesson 7.8, Improper Integrals, we're going to examine what happens when we evaluate integrals that have some kind of discontinuities, such as vertical asymptotes, or what happens when we evaluate integrals off to infinity or negative infinity, where we can't cleanly use the fundamental theorem of calculus. Before we begin our study of improper integrals, let's take a look at 3 examples of them and how to properly evaluate them. The 3 most common type of improper integrals are the ones you see here, ones that involve lower or upper bounds with infinity or negative infinity. So before we get started with our examination of some actual examples, I do want to show you what will happen and how we set it up when we do have infinity or negative infinity as an upper or lower bound. In our first example right here, you see that we have infinity as an upper bound. The way we're going to deal with that is by actually changing the problem so that we're going to from a to b of f of x dx. Now you might be saying, well, that doesn't seem right. What happened to the infinity? And we handle that situation by simply putting a limit as b approaches infinity out front of the integral. Once we integrate this, we'll plug in b, we'll plug in a as per the fundamental theorem of calculus, and then what we'll end up with is a limit problem that hopefully we'll be able to handle. Right here in the middle example, you see that we have negative infinity as a lower bound, and we're going to handle that much the same way as the first one. We're going to do a limit as a approaches negative infinity, and again, we're going to change the integral so that we're integrating from a to b of whatever function we're looking at. And clearly, after we integrate that, we'll apply the fundamental theorem of calculus, and we end up with, again, just a limit problem, so no big deal there. Now, the biggest example is going to be what happens down here in our third example. Here we have negative infinity and positive infinity. Those of you taking AP statistics, this is the kind of situation we would run into with a normal curve if we want to know the area under the entire normal curve from what we've been typing in the calculator is negative 99999 to positive 99999. Really, we're going negative infinity to positive infinity. The best way to handle this is to choose some arbitrary breaking point. A lot of times we use 0. But what we're going to do is we're going to do a limit as a approaches negative infinity. So we're going to go from a to some arbitrary value. Again, generally we use 0 if that doesn't cause any problems. So we'll have that integral plus now we're going to handle the upper bound, which is the limit as b approaches infinity. And this time I'm going to go from that arbitrary breaking point up to b. We learned a while back that when we integrate from a to c and then from c to b, really we can split it into 2 and then just add the 2 integrals together. So that's what we're going to do here on the bottom situation. Well, now that we know that, why don't we go ahead and take a look at some actual examples. In our first example, we're going to take a look at the integral from 1 to infinity of this 5 over x cubed dx. Now, the directions tell us to determine whether the improper integral converges or diverges. And what that means, if it does converge, what we're saying is that it does approach a certain value. This one is going off to infinity, so if it converges, we're saying that it approaches its horizontal asymptote quick enough that we can say it actually approaches a certain value. It won't go beyond that, and that's going to be the value of our integral. On the other hand, if it diverges, it does not approach that horizontal asymptote quickly enough, and in essence, the integral is going to grow without bound. We're not going to be able to find an upper bound for its growth, and all we're going to end up with is we can't tell what it equals. So let's take a look at this. It'll become clear as we go throughout the problem whether it does actually converge or diverge. As we said previously, we're going to actually rewrite this as the limit as b approaches infinity of 1 to b of, I'm going to rewrite this as 5x to the negative 3 dx. All right, so no problem so far. This is an integral that we can handle, And if we do go ahead and integrate this, of course, what we're going to end up with is negative 5 halves x to the negative 2 from 1 to b. All right, well, that negative 5 over 2 is a constant, and I'm going to go ahead and move that out of the way here. But if I go ahead and apply the fundamental theorem of calculus, what this is actually going to say is going to be 1 over b squared minus 1 over 1 squared, which I will just write as 1. So I've applied the fundamental theorem. I've plugged both these in. All I need to do now is find the limit as b approaches infinity. And, if you consider, I know in reality you're not plugging infinity in, but if you think about it that way, this essentially is going to become 0. And so what we end up with here is negative 5 halves 0 minus 1. And so this integral right here, this definite integral, is going to end up evaluating to 5 halves. I certainly welcome you to plug this function in your calculator and see for yourself that it does approach its horizontal asymptote quickly enough, as we say. That's rather informal, but it'll work for now. And we do end up with 5 halves as our integral. Our second example is very similar to the first example. You can see, again, we're going from 1 to infinity, and we have a very easy integral to evaluate. So I'm not going to spend a lot of time on this one. Let's just go ahead and write it out and see what happens here. Again, we're going to do the limit as b approaches infinity from 1 to b. I'll rewrite this as 4x to the negative 1/4 dx. And we'll just go ahead and integrate this, and we'll take it from there. So we're going to end up with the limit as b approaches infinity. This 4 I'm going to take and, kind of move it out front here. When I do integrate this, the constant is going to become 16/3, simply because this fraction right here is going to turn into x to the 3/4 times 4/3. So there's the 4 and the 4/3 over there. And again, I'm going to evaluate this from 1 to b. Now, doing this, I'm going to have 16/3. Again, I'll have the limit as b approaches infinity. Don't forget to write your limit statement. That is very important. That limit statement takes the place of the infinity as one of your bounds. So you can't just disregard it. Anyway, if we go ahead and plug these in here, what we're going to end up with is b to the 3/4 power minus 1 to the 3/4 power, which is just 1. And take a look at this. When I plug infinity into my result of the integration here, infinity to the 3/4 power is actually going to escape into infinity. And essentially what I have, I hesitate to write this. It's not exactly right. But if I write 16/3 and then infinity minus 1, clearly I can't evaluate that. This integral does diverge, and I'm not going to be able to evaluate it, short of saying that it diverges. Well, let's take a look at another example now that we've seen a converge and a diverge, and we'll see what happens with the next one. So, our third example is a pretty interesting example. It's not just a simple integral like the first two examples were, but realize it's not going to be a very difficult integral to do necessarily. Of course, before I get into anything else, I need to go ahead and take care of the fact that this is an improper integral. I'll replace that infinity with a b and put a limiting statement here. And so I end up with this as my new problem. Now you should be able to look at this and figure out some way or another to be able to integrate this. And hopefully your thoughts go back to a U-substitution type situation so that u will equal the denominator and du, by coincidence or whatnot, will equal the numerator. So if I go ahead and rewrite this with my U-substitution, of course 0 and b aren't really going to be the correct bounds when I do my U-substitution, but I'll kind of like pretend that this says 0 and b for now. And we'll just, pretend like that and see how it works out. Of course, this is going to turn into 1 over u du, which you should recognize is simply an integral that brings you back to a natural log. So if we do that, this is simply going to be the natural log of u, which in this case is the natural log of 1 plus e to the x, and we're going to evaluate this from 0 to b. Well, let's see how this looks when I use my fundamental theorem of calculus and plug in my upper and lower bounds. What I'm going to end up with here is the natural log of 1 plus e to the b, and I want you to think of that as essentially e to some crazy huge power. I have a feeling this is going to be unbounded, but just for the sake of brevity, let me finish this out. It'll be minus the natural log of 1 plus e to the 0. All right, well, if we go ahead and handle the situation here, again, b will go to infinity. We have the natural log of 1 plus e, well, to the infinity, kind of. And this will simply be, of course, minus natural log of 2. Natural log of 2, no problem. I got that. That is not an issue. But this part right here, where I'm going to plug infinity in there, again, this is going to be unbounded. I'm not going to be able to evaluate it. And all I'm going to be able to say for this problem is that the integral does, in fact, diverge once again. So an interesting example, a little more difficult this time. Not a lot more difficult, but gives you an example of something different than just a constant over some variable. It's a u du. We should be used to these. Example D is quite a bit different than the first 3 examples we did. As you notice, there is no infinity in the bounds. We're simply going to integrate the natural log of x squared from 0 to e. At first glance, that doesn't seem like there's going to be an issue here. Can I just integrate and plug those in? But when you think about the graph of the natural log of x squared, it's going to go something like this. And, well, we can go up to e. That's no problem. But starting at 0 does present a problem. 0 is not in the domain of this function. And, in fact, the function is asymptotic to x equals 0. So, although you don't see an infinity here, we are going to have to do a limit here. And we're going to do the limit as a approaches 0, being as how 0 would cause a lot of issues to happen here. We'll just resolve it by having a placeholder, essentially. So our problem is going to turn into this. If it's okay with you, I'm going to take this exponent and just drop it down out front. So I have 2 times the natural log of x dx. Now, 2 being a constant, again, I'm going to take that and drop it way out front of the problem. And I'm going to end up with 2 times the limit as a approaches 0 of from a to e of the natural log of x dx. Now, back when we learned about the integration by parts, I told you that this was a good integral to memorize. We can certainly go through and do the u and the du and the dv and the v and do all the integration by parts. But if you have the integral of the natural log of x memorized, that's going to make this a very easy problem for us to deal with. So I'm going to skip the integration by parts. I do have this memorized, as you should. So I'm just going to go ahead and handle this out. The integral of the natural log of x is simply going to be x natural log of x minus x. And we are going to integrate this from a to e. Doing this, I'm going to keep everything the same, except I'm just going to plug in some values now. When I plug e into this, I'll have e natural log of e, which is simply just going to be e, and then minus, I'm going to plug e in here too. So e minus e, that's going to 0 out clearly. And then I'll subtract, when I stick a in here, I'll have a natural log of a minus a. So far so good. Of course, this is going to 0 out. So what I'm going to end up with is 2, and then I'll do the limit as a approaches 0. What I'm going to end up with here, if I distribute the negative, I'm just going to go ahead and rewrite this as a minus a natural log of a. I'm just going to reverse them because of the negative sign here, if I distribute that. All right, well, if I plug 0 in, it's pretty clear to see that I'll just start with the 0. But when I plug 0 in here, I'm going to write this, But understand that this is not formally correct. I'll have 0 times the natural log of 0. Now, the natural log of 0, I can't really evaluate that. Fortunately, I'm multiplying it by 0, so it essentially is going to 0 out. And what I'm going to end up with is 2 times 0, and the integral of this will be 0. Feel free to check this on your graphing calculator. You can do the integral yourself, and you'll see for yourself that this integral does, in fact, evaluate to 0. The final example from the first section of our notes is one that looks rather intimidating, but I'm going to argue really is not all that bad. We're going to be integrating this thing from 1 to 3, which at first glance doesn't seem like there would be any issues at all. But take a look at the domain of this function. Clearly, the domain x does not exist at 2, which is smack dab in the middle of what we're trying to integrate here. So, how are we going to resolve this issue? Like our third evaluation technique, we're going to break this integral somewhere in the middle and then evaluate 2 separate limit problems. In fact, it's going to look kind of like this. Since we're going from 1 to 3 and the domain doesn't exist at 2, 2 is going to be where I break this. It's going to look like this. I'm going to say the limit as b approaches 2 from 1 to b of this function. So that'll be the first part of the function. And then what I'm going to do is I'm going to add that to the same integral, but the limit as a approaches 2 this time. So this time that will be the lower bound, and I'll go from a to 3 again of this function. So nothing too difficult here. Conceptually, the only problem is I needed to find where this integral is breaking, and it is breaking at 2. So if I go through and evaluate all this now, I'm going to save some of the trouble. I'll leave the integration as an exercise to you. Although if done correctly, you should get a result similar to this. There will be a negative 6/5 that will be present in both of these when I integrate them. So I'm just going to pull that out of both parts. Over here, I'll have the limit as b approaches 2. The integral of this is simply going to be, without the negative 6/5 there, it's going to be x minus 2 to the negative 5/3. All right, and of course I'm going to evaluate that from 1 to b. And then I'm just going to do the same thing over here. It'll be the limit as a approaches 2. Of course, the integration is going to be the exact same. All that's going to be different here is my bounds. I'm going to go from a to 3. All right, so that's what the integration of this is going to look like. If I go through and start plugging in my values, what's going to happen here? I'll have the limit as b approaches 2. I'll stick b in here, and what that'll do is essentially give me 1 over, I'll write it this way so that it might be easier to see, b minus 2 to the 5/3, all right? And then I'll subtract whatever I get when I plug 1 in there. In fact, when I do plug 1 in there, what I'm going to end up with is a +1. So that's going to be the first part of all this. And I'm going to get a little parentheses happy, but it'll all work out in the end. You got to love parentheses. There's nothing that's much more fun and exciting than those, so it's a positive thing. Over here, of course, I'm going to end up with the same thing, except I'm going to plug in the 3 first. And when I plug in the 3, that's simply going to give me 1, a positive 1. And then I will plug in a minus 2 to the negative 5/3. For some interesting reason, I decided to not turn it into a fraction like I did the first time, but whatever. It's all going to work out the same. What I'm going to end up with, negative 6/5. The limit is b approaches 2. If I plug that in here, what I'm going to end up with is essentially an undefined thing. So I'm just going to write undefined, but there's still my +1, so that's wonderful. Over here, I'm going to have plus, there's my other 1, minus, and when I plug 2 in here as my limit, You can go ahead and try limiting yourself. You will see that this is also undefined. And as much as I would love to cancel out these two undefineds, there's really no mathematical operation that will allow that to happen. And as soon as I hit one undefined, I actually could have stopped right there and said, this integral is going to diverge. I'm not going to be able to find an actual value for it. And there we go. Now, the next two examples that we're going to take a look at are special types of integrals. And I would like to talk to you about these harmonic series, if you will, before we actually do the next two examples. Well, it's always good to end a chapter with a few easy problems, and that's what we're going to do here. What we do is we're going to call this a P-series type of integral. We're going to examine these a lot more when we get to studying series and sequences in our next chapter. But for now, just take my word that this is called a P-series. It's generally written as some constant divided by x to some power, and that power is the P from which the P-series gets its name. Well, here's a very, very surprising fact. These are very simple to do. If that exponent in the denominator is greater than 1, then we can rest assured that this integral is going to converge. In fact, not only is it going to converge, it is going to converge to the value 1 over p minus 1. That's a beautiful fact right there, and it might hearken you to series and sequence sums that you've learned back in pre-calculus or in the past. As well they should. It's essentially a ratio. However, if p is less than or equal to 1, in that case, this will diverge. Now, of course, you are certainly welcome to try these problems out the long way using the limits, but I think you'll find that this table summarizes it very, very nicely for you. Now, this being said, let's take a look at a couple of examples of P-series and how they'll work. Before we begin our first P-series example, I want you to take a quick look back up at examples A and B that we worked out earlier in these same notes here. Hopefully what you'll notice is that examples A and B both were P-series examples. Clearly they were just done before P-series were introduced. However, if you take a look at those, on example A, you'll notice that P is 3. 3 is greater than 1, and certainly example A did converge. Example B, you'll notice that the P was 1/4, which if you take a look at our table over here, certainly 1/4 should cause it to diverge, and in fact it did diverge. So A and B are good examples of P-series, but let's go ahead and take a look at this now that we know the little shortcut going on. If I look at this, what I can do is I can say that this is approximately the same as the integral from 2 to the infinity of 1 over, now instead of calling this x minus 1, just for simplicity's sake, I'm going to call it x to the 1/2. A lot of people are going to argue and say, well, you can't just throw the negative 1 out. That changes everything. I agree it does change certain things, but it's not going to change the speed at which this function will get close to its asymptote. So that minus 1, in the long run, as we go towards infinity, this minus 1 becomes essentially irrelevant, and we end up with this as our integral. Now, of course, in this situation, we have p equals 1/2, 1/2 being less than 1, less than or equal to 1, I apologize. And so clearly, this integral is going to diverge. Now, of course, I certainly welcome you to do this as a limit problem if you want to do the limit as b approaches infinity of 2 to b of x to the negative 1/2. I certainly welcome you to do that. I think what you'll find, however, is that this integral does in fact diverge, as we found with the P-series test. Let's go ahead and take a look at one more example before we're finished with these notes. So, example G certainly looks very intimidating. What I'm going to argue is that it's actually a very easy problem if we use an approximation for this. If you want to actually write this out, this is the integral from 1 to infinity. I could write this as x to the 3/2 plus x to the 1/2. But to be perfectly honest, as the limit of x goes to infinity, what we'll find is that this 1/2 is essentially irrelevant when faced up against x to the 3/2. So what I'm going to do is I'm going to approximate this as the integral from 1 to infinity of 1 over x to the 3/2 dx. Clearly, this is a p-series with p equals 3/2. 3/2 is, of course, greater than 1, and so what I can be sure of is that this integral will converge. I can clearly find the value to which it will converge. I could just go 1 over p minus 1 and find it that way, but just saying that it does converge does answer the original problem. So as you can see, p-series are very easy situations to work with, but on the whole, remember that you have an improper integral if you have an integral that is either has infinity or negative infinity as an upper or lower bound, or if you have an integral which covers up to or even both sides of a vertical asymptote. If either of those situations are true, all you really need to do is just make a limit statement out of it, and then it becomes a type of problem that we could have done back when we were actually studying limits. Hopefully you don't have too many problems with this. It is a very important lesson, although it might not seem so difficult. The importance is certainly there. And so, good luck with your 7.8 assignment.